Okay, so come back to the next one. Hope we are understanding the things, right, and thinking all this point. I am solving many problems for you. It will help you a lot, right, to understand that all these things whatever is there. And next we will take a voltage pulse given by this, right. So it is given that V t is equal to 0 for t less than 0. That means past history, right, and when V t is equal to 2 t, there will be linear relationship with time in between 0 and 2 second, right. And your another thing is given that V t is equal to 4 into e to the power minus t minus 2 when t greater than 2. It is 2 less than t. In other way, this one you can write when t greater than 2, right. So this way your what you call is applied across a 10 microfarad capacitor. I mean this kind of voltage applied to a 10 microfarad capacitor for this time duration. To sketch the voltage across and current through the capacitor, that means you have to sketch the voltage across the capacitor as well as current passing through the capacitor. This you have to sketch, right. Now this voltage is given, so this voltage you can easily sketch, right, from you can sketch from 0 to infinity, because t greater than 2, that means in between 2 t 0 to your what you call 2 0 to 2, and then this exponential thing for 0 to 2 to infinity, right. When you put your later we will see this. So first let me clear it, right. So we know it is 10 microfarad capacitor, right. C value is given 10 microfarad. Now I is equal to C into dV by dt. So for t less than 0, so it is given V t is 0 for t less than 0, that is a past history. So I is equal to 0, right. Now next one is that in between 0 and 2, that C is 10 into 10 to the minus 6 microfarad it is given, and it is your V t, that your V t is equal to 2 t. That means my dVt by dt is equal to 2, and that 2 is here, that is C into dV by dVt by dt, right, it is 2. So that means, and C is actually 10 microfarad, so 10 into 10 to the minus 6 your farad. If you multiply this, it will be 20 micro your ampere your what you call the current, right, in between that interval 0 and 2. And now next one is similarly, let me clear it. Similarly, that dV by dt, you take the derivative of this one, just 1 minute, that this is V t is given, this expression is given 4 e to the power minus t minus 2, you take the derivative of this one, right. So if you take the derivative of this one, it will become minus 4 into e to the power minus t minus 2, right, and C is 10 into 10 into 10 to the power minus 6. So and it is equal to minus 40 to the power t minus 2 microampere for t greater than 2, right. So this way you calculate, all V's are given, just take the derivative. Now question is that voltage plot, this is my your in between your what you call V is equal to 2 t, just 1 minute, let me move little bit up, right. So if we move little bit up, right, this V t. So here this is my V t, actually it will be 2 will be somewhere here, right. So it is V t is equal to 2 t, and next one your what you call, and from 2 20, this is in between 0 and 2, and when t greater than 2, your V t this was given 4 e to the power minus t minus 2, this was given, and this is the plot of your that V t, this one, it is given in the first in the problem, right. So this is your plot of V t, in this is t is second, right. So this is V t, and similarly if you plot I t for I that for your for t less than 0, it is 0, otherwise for in between 0 to 2, it is 20 micro your ampere, and if it is greater and t is greater than 2, right. So it is minus 40 to the power minus t minus 2. Now when t is equal to 2, suppose when t is equal to 2 second, right, then this your I t is t is equal to 2 is equal to, it will be minus 40, because it is the power 0, it will become when you put 2. So it will be minus 40 microampere at t is equal to 2, right. So, that means first one, if you see that 20 microampere, it is basically your constant. So, in between 0 to 2, right. Let me move it little bit up. So, this is your 0 to 2, that is your 20 microampere. Now, plot is not completed, this is your minus 10, minus 20, then minus 30, then it will be somewhere minus 40, right, and it will start from minus 40 somewhere, and then it will go like this, right. So, this is your sketch of your what you call that current. So, that is what and your what you call this equation, from this equation, this is the plot, right. So, this is, hope you have understood this, right. Next one is series and parallel capacitors. So, figure 11, it shows n number of capacitors are connected in series. Suppose you have this figure, you have n number of capacitors, and across each capacitor its voltage is V1, V2, V3 up to Vn. In between some kth capacitor is also there, right. I mean some if you make V1, V2, V3 like this, somewhere some plus dot some kth capacitor is also there, and voltage there is Vk, right. So, and n is the last one, right. I mean it is 1, 2, then 3 up to kth capacitor, then nth, right. So, somewhere kth capacitor is there, right. So, let me clear it. So, all these capacitors are in series. So, now and total voltage here is V. So, from that one thing is there, let me write down for you. For this one thing is there, that your V is equal to V1 plus V2 plus Vk plus Vn, right. This is your what you call that voltage V, this is the supply voltage V, right. Now, let me clear it. So, now if you want to make here one your what you call that all this is an equivalent circuit. So, whatever voltage is applied here, this capacitor will be, say it is Ceq, and all this voltage is V. So, so naturally only current flowing is I, naturally voltage across this also will be V, right, and this capacitor is a Ceq, equivalent circuit. So, let me clear it. So, this is series connected and equivalent circuit of the series capacitor, this is equivalent circuit, and this is Ceq, right. So, V is equal to, I told you, V1 plus V2 up to Vn. Now, for kth capacitor, we know the voltage V is equal to 1 upon C T0 to T IT dt, right, we know that. So, earlier we have studied this. So, this one instead of V we are writing for kth capacitor Vk, and value of kth capacitor is Ck, 1 upon Ck, time is T0 to T IT dt plus Vk T0, right. I told you in the past at some time, say minus infinity, some time that your what you call voltage across the capacitor, in its voltage across the capacitor was 0. So, that is why Vk minus infinity was 0, only Vk T0 is kept here, right. So, this is equation 13. So, this is for Vk, that means V1 is equal to 1 upon C1 T0 to T IT your what you call dt plus V1 T0. Similarly, V2 is equal to 1 upon C2, then T0 is equal to your T I T0 to T IT dt, then V2 T0 like this, because all the capacitors are in series. So, let me clear it. Therefore, we can write V is equal to 1 upon C1 T0 to T IT dt plus V1 T0. This is for capacitor 1. Similarly, for capacitor 2, it is 1 upon C2 T0 to T IT dt plus V2 T0. So, similarly, for nth capacitor up to n 1 upon Cn T0 to T IT dt plus Vn T0, right. Now, your now you next term you can write, you take 1 upon C1 plus all collect all the term T0 to T IT dt, right. Therefore, 1 upon C1 plus 1 upon C2 up to 1 upon Cn T into bracket close into T0 to T IT dt plus V1 T0 plus V2 T0 up to Vn T0 you can write, or you can write 1 upon Ceq, that means C equivalent T0 to T IT dt plus Vt0. This is equation 14. Now, Vt0 is equal to V1 T0 plus V2 T0 plus Vn T0, right, whatever is there, because circuit is like this. This is the circuit, all initial T is equal to T0, it is V1 T0, V2 T0, Vt 30, and that means V T0 here will be V1 T0, V2 T0 sum of all, right. So, here it is your, that is your Vt0 is equal to all these things. Therefore, if you compare this equation 14 with equation your with this equation, right. So, that means 1 upon Cq is equal to 1 upon C1 plus 1 upon C2 up to 1 upon Cn, that is all summation of reciprocal. It is something like this when we are obtaining your resistance in parallel. So, same thing, but capacitor, when capacitor will be in series, that calculation will be the way we made parallel resistor your combination when you are trying to find out equivalent resistance for parallel resistor for series connection of capacitor. It is just your what you call just opposite to that, opposite to the resistors of parallel, that your what you call the way you obtain mathematically. So, it gives the equivalent circuit for the series capacitor. Note that capacitor in series combine in the same manner of resistance in parallel. The way we find out equivalent resistance in parallel, right, for capacitor we can compute same way when they are in series. That means here you have capacitor, your what you call, here you have capacitor C1, C2, C3, then Cn, and this capacitor is C equivalent, right. Therefore, 1 upon Cq, when capacitors are in series, it is 1 upon C1 plus 1 upon C2 plus 1 upon C3 plus 1 upon Cn, right. I mean, it is same calculation the way you calculate resistor in parallel, capacitor also have to calculate same way when they are in series, right. So, this is, and this capacitor is your Ceq, and 1 upon Ceq is equal to this one, right. So, let me clear it. So, that is we have made, right. So, from that you can find out, if you know C1, C2, C3 all, you can calculate Ceq, right. So, this is what we get for series connection. Now, if capacitors are connected in parallel, right, it will be your what you call, when they are connected in parallel, it will be like same manner when you calculate resistors and in series, right. So, in this case a current source is taken just for easy analysis, right, and C1, C2 up to Cn capacitors are in parallel, right, and voltage V. So, all are in parallel. So, voltage C1, C2, C3 that your what you call, this voltage is given V, because all are in parallel, right. So, that means voltage remains same, and this is C equivalent for parallel connection. So, if you go for mathematics, if you that I is equal to this current I is equal to I1 plus I2 up to In, right. So, this current I is equal to I1 plus I2 plus I3 up to In, and I1 is equal to C1 into dV by dt, because C2 because voltage are in parallel. So, voltage V will be same across all the capacitor, right. So, that is why it will be C1 into dV by dt plus C2 into dV by dt up to Cn into dV by dt, or you take, I can write we can write I C1 plus C2 up to Cn dV by dt, or I is equal to Cq dV by dt. That means Cq is equal to C1 plus C2 up to Cn, sum it up. That means when resistor are in series, we are summing R1 plus R2 up to Rn, say. When the capacitors are in parallel, at that time their value will be that thing will be summed up, right. Just your what you call, it is the way they are in a manner when you add the resistance in series. In the case of capacitors are in parallel, you have to just add them up, right. So, note that capacitors in parallel combine in the same manner as resistor in series. So, then this is the your what you call, this is the equivalent circuit, and Ceq is equal to C1 plus C2 plus C3 up to plus Cn, right. So, if you take this example, find the equivalent capacitance seen between terminals 1 and 2 of the circuit. You have to find out the equivalent capacitor. Look here, if you look at the circuit, that 5 microfarad and 20 microfarad are in series. That means, you have to combine it like the way you do it when resistors are in parallel. So, it will be equivalent will be 5 into 20, right, divided by 5 plus 20, because these two are in series, microfarad, microfarad, right. So, it will be basically your it is 25 and 100. So, it will become 4 microfarad, right. So, equivalent will be 4 microfarad. Therefore, what will happen that their equivalent is 4 microfarad, those, that means this 4 microfarad, then 6 microfarad and 20 microfarad are in parallel, Parallel means just a combination, just addition. So, this equivalent of this 4 microfarad. So, its parallel means it is a combination. So, it is 4 plus 6 plus 20 microfarad, that is your 30 microfarad, right. And just if you add it, it will be like this, right. Therefore, and with that, the 60 and 30 again are in your what you call are in series. So, at that time you have to go for like a parallel combination, right. So, this will be 30 microfarad, and again we will see 60 and 30 if you make it add it up, because they are in parallel. So, they are in series. So, at that time it will be 60 into 30 by 60 plus 30, that is 90. That means, it will be your 20 microfarad, equivalent will be 20 microfarad, that will be CEQ, that will be the answer. So, a solution is there in your later, right. So, if you look into this 20 and 5 are in parallel series. So, it will be 4 microfarad. Now, 4 microfarad is in parallel with 6 microfarad and 20 microfarad capacitor, all are written here, and their combined will be 30 microfarad. You add them up. Now, 30 microfarad capacitor in series with 60 microfarad capacitor. Therefore, you have to, again, series means it is like a your find equivalent resistance is parallel. For same way, for series one you have to make it for capacitor. So, 30 into 60 by 30 plus 60. So, 20 microfarad, right. Next one is another example. So, this is the answer. Another example is for the circuit shown in figure 14, determine the voltage across each capacitor. So, this the circuit is given 300 volt, this is V1, V2, this voltage is V3 and V4, all the capacitors value are given 20 microfarad, 30 microfarad, 40 microfarad, and again here it is 20 microfarad, right. This look, this 20 and 40 they are in parallel, right. So, when how will that 40 and 20 microfarad are in parallel. So, what you do, you add them up 40 plus 20. So, 60 microfarad, right. Then 60, 30 and 20 are in series. First these are parallel, you add them up 40 plus 20 60 microfarad, and then 60, 30 and 20 they are in series. That means, you have to find out the equivalent one, that CEQ will be 1 upon C1 plus 1 upon C2 plus 1 upon C3, equivalent that one to the power minus 1, that will give you 10 microfarad, because here these two are in parallel, right. So, their equivalent is 40 plus 20, right, is equal to 60 microfarad. Now, 20, 30 and 60 you are what you call they are in series. That means, 1 upon CEQ say is equal to 1 upon 20 plus 1 upon 30 plus your 1 upon 60. That means, CEQ is equal to 1 upon 20, hope it is readable for you, I am drawing on the circuit, 1 upon 60 to the power minus 1, right, just reciprocal of that, that is why minus 1 is given here, right. So, let me clear it. So, that is why you get your what you call 10 microfarad. Now, total charge is Q is equal to CEQ into V, right, because this is CEQ and total charge Q will be CEQ into V. V is given 300 volt and it is 10 microfarad. So, 10 into the minus 6 farad into 300 coulomb. So, 3 into 10 to the power minus 3 coulomb, that is Q, right, total charge. Now, this actually it will be is, this is the charge on 20 microfarad and 30 microfarad capacitor, because they are in series with 300 voltage source, right. So, this total charge Q, just let me clear it, right. So, 20 microfarad and 30 microfarad capacitors are in series. If you look into that, 20 and 30 microfarad capacitors are in series. Actually, whatever Q we have found out, that is basically the from equivalent capacitor, that is the total charge, right. But as 20 and 30 microfarad capacitors are in series, right. Therefore, this is that your what you call, this is the charge on 20 and your this is actually there will be an is, right. This is the charge on 20 and microfarad and 30 microfarad capacitors, because they are in series with the 300 volt source. Therefore, we know Q is equal to Cv from the formula. So, V1 will be Q upon C1. So, Q you have got this one. So, this is 150 volt and V2 will be Q upon C2. So, it will be 100 volt, right. So, as we have got V1 and V2, that is 150 and 100 volt respectively, we can easily find out V3 and V4, right, using you can apply KVL also. So, note that applying KVL. So, now if you apply KVL in this equation, if you apply KVL in this in this circuit, if you apply KVL like this, I am moving clockwise. So, it will be plus V1 plus V2 plus V3 minus 300 is equal to 0. That means, my V3 is equal to your 300 minus V1 minus V2, right. It is V1 minus V2, and these two capacitors are in parallel. That means, V3 is equal to V4, right, because these two are in parallel. So, go to that calculation. So, it is with 300 minus, so 50 your what you call, it is 50 volt. V3 is equal to, and V3 C3 and C4 are in parallel. So, same voltage. So, V3 is equal to V4 is equal to 50 volt, right. So, next is consider the circuit shown in figure 15. Prior to t is equal to 0, the capacitor C1 is charged to a voltage V1 is equal to 100 volt, and the other capacitor has no charge, that is V2 is equal to 0, right, that is uncharged. At t is equal to 0, the switch closes. Compute the total energy stored by both capacitor before and after the switch closes, right. So, this is the diagram. It says that before closing the switch, this voltage V1 was your what you call 100 volt and V2 was 0 volt, right. This one is uncharged, and you have to calculate before closing the switch what is the total energy, and after closing the switch what is the total energy. Here we will see some funny thing, right. So, question is that before this your what you call this 1 microfarad, both are 1 microfarad each, but here V1 is in its voltage is given before switch is closed, it is 100 volt, but here V2 is equal to 0. So, for this one it will be half C1 V1 square right, that is half into 10 to the minus 6 into 100 square, because V1 is 100 given, and here it is 100 volt is given, that V1, and here it is 0, right. So, before this your hold on. So, before this your initial store energy, and before closing the switch, half C1 V1 square. So, it is coming 5 into 10 to the power minus 3 joule, and second case voltage V2 was 0. So, half C2 V2 square means 0. So, directly we are writing it is 0. Therefore, total energy W is equal to W1 plus W2, that is 5 into 10 to the power minus 3 joule. This is the value. Now here the thing. Now, to find the voltage, and store energy after the switch closes, right, we make use of the fact that the total charge on the top plates cannot change when the switch closes, right. We have to make use of the fact, right. In fact, this is true, because there is no path for charge to leave the upper part of the circuit, right. So, idea is something like this. So, we make use of the fact that the total charge on the top plates cannot or what you call change when the switch closes. So, in fact, this is a true because there is no path for charge to leave the upper part of the circuit. Now the charge stored on the top plate C1 prior to T0 is given by Q1 is equal to C1 into V1, that is C1 is 1 microfarad. So, 1 is minus 6 into 100, that is 100 microcoulomb, that is the charge stored on the top plate C1, right. So, let me clear it, and similarly for Q2 charge on C2 is equal to 0, the initial charge on C2 is equal to actually 0, right. So, I should not write C2 is equal to 0, initial charge on C2, right, better I write is equal to your 0, right. So, otherwise it will carry different meaning, right. So, hence Q2 is equal to 0. The thus after the switch closes, the charge on the equivalent capacitance is, when switch is closed, the charge on the equivalent capacitance is, it will be Q1, it will be Q1 plus Q2, that is also 100 microcoulomb, right. So, that means it is 100 microcoulomb. Now, also note, after the switch is closed, the capacitors are in parallel. We have an equivalent capacitance. I mean, when look, if you go back to the circuit, that when switch is closed, say it is when switch is closed, this C1 and C2 are in parallel. That means, and both are equal, right. That means, it will C1 plus C2, that is, it will become 2 microfarad, because both are in parallel when switch is closed, right. So, in this case, sorry, let me clear it. So, here, so these capacitors are in parallel and we have an equivalent capacitance is 2 microfarad. Now, the voltage across the equivalent capacitance is now V eq will be Q eq upon C eq. So, V Q eq 100 microcoulomb and C eq is equal to 2 your what you call microfarad. So, it is basically 100 by 2, because it is microcoulomb and it is microfarad. So, micro 10 to the minus 6 will be cancelled, right. So, it will be 50 volt, right. Now, question is, of course, after the switch is closed, V1 is equal to V2 is equal to Vq, because they are in parallel. So, both voltage will be equal. Now, we compute the stored energy with the switch closed. Now, as we have switch closed, W1 will be half C1 Vq square, it will be half into 10 to the minus 6, 1 10 to the minus 6 into 50 square. So, 1.25 into 10 to the minus 3, that is joule, right. Similarly, W2 is equal to half C2 Vq square, half into 1 into 10 to the minus 6 into 50 square, that is 1.25 into 10 to the minus joule, minus 3 joule. Now, total energy, if you sum it up, W1 plus W2, it was 2.5 into 10 to the power minus 3 joule. That means, before switch closed, it was 5 into 10 to the power minus 3 joule. That is, when switch was before closing the switch, but after closing the switch, it is coming 2.5 into 10 to the minus 3 joules. That means, energy balance is not there. That means, some 50% of the energy is missing, then where that energy has gone, right. That is why this problem I have taken, that where that energy has gone. So, to do this, to justify this, right. So, we see that the stored energy after the switch is closed is half of the value before switch is closed, right. So, what happened to the missing energy, because 50% is missing. The answer to this question is that it is absorbed in the your what you call, it is absorbed in the I will not put parasitic resistance, it is absorbed in the your what you call parasitic inductance, right. It is parasitic inductance, it is impossible to construct, right. So, this one is strike it off, right. So, it is impossible to construct capacitor that do not have your what you call that parasitic resistance or inductance. How? So, some parasitic effect is there. For example, a more complete circuit model of a capacitor is shown like this. This is my C, but with that Rs, Ls and Rp is there, right, because conducting foils, right, you have some your what you call some resistance. So, if you take the resistance, that will be Rs, right, for conducting plate of the capacitor, we are neglecting it, and as the current flowing to the capacitor, there must be some magnetic field. Because of that, some parasitic inductance also will be there, although their value is very small, and in between that no material is a pure insulator, right. Some conduction will be there to your, because dielectric we are taking in between the parallel plates, but some conduction will be there. Because of that, some Rp will be there, right, because that Rp resistance we take, right, this Rp. So, that is why this is actually as a whole the your what you call that for a parallel plate capacitor, but we neglect Rp, we neglect Ls and we neglect Rs also. Otherwise, that 50% energy missing, if we had considered that, you should have found actually it is here in the parasitic inductances, right. That because it is missing means, that means somewhere it has gone, that means somewhere it is stored. So, it will be in the parasitic inductances. That is why this example is taken right. This is actually complete diagram of a parallel plate capacitor, but RS, LS and RP will be neglected. Now, all this write up is here, whatever I told, right, all this write up is here. So, whatever I said, it is okay, but you just go through it, right. So, I am moving it little bit slowly. So, RS, L, RP are the parasitic elements. If we include the parasitic inductance in the circuit model, we would have not have missing that 50% energy, but we have not. This example intentionally I have taken to give you a flavor that why that your what you call energy has gone, right. So, another one will take this thing, the voltage pulse described by the following equations is impressed across the terminals of 0.5 microfarad capacitor, right. So, Vt is 0 volt for t, actually here it will be just 1 minute, it will be t less than, right, this way you make, right. So, 0 volt for t less than 0 and 40 volt for in between 0 and 1 second, and 4 e to the power minus t to t minus 1 volt in between 20 your what you call your in between 1 and infinity, right, t greater than 1, right. So, what we have to do is that we have to find out all this, derive the expression for the capacitor current, power and energy. This is number A. Sketch B, sketch the energy as function of time. C, specify the interval of time when energy is being stored in the capacitor, right. I mean, you have to, when energy is stored or dissipate or what you call, you have to specify that time, or specify the interval of time when energy is being delivered by the capacitor, that also we will see that based on certain convention we will find easily. Evaluate the integrals 0 to 1 p dt and 1 to infinity p dt and comment on their significance. So, thank you very much, we will be back again.